So we're going to get a little bit lower level right now in this course. We're going to get lower level in this lesson. We're going to talk about what buffers are and what a buffer overflow is, and how you can use a buffer overflow to exploit and gain control of a process or a device. And first, let's talk a little bit about what buffers actually are. Buffers are containers for data. And really, when we're talking about buffers, we're talking about the C programming language. This is a programming language that has very manual memory management. As you bring in messages and you parse these messages, you have to have these temporary storage places to keep information as you're parsing the data. And so your buffers are your containers for this data. And in this case, we're doing something called a linked list, where we have a buffer and then we have a pointer that points to the next structure that has the same buffer in it, and so on. And when you do a buffer overflow, you're stuffing too much information into that container. So we've only set aside 14 characters or 14 bytes to hold that information. And when you write over this buffer, you are writing into the next field of that structure in this case. So you will have lost that information that you had to be able to link those buffers together. And this is a buffer overflow. In this case, we've lost track of our linked list data structure. But you can do things that are much more damaging, which you'll soon see. And this is just showing how we're doing it, is that you're using an operation or a function in C, for instance, like a strcpy or sprintf, and you're writing to that buffer, and if you're not careful with your boundaries, you can actually overwrite that data and write over to the end of the buffer and into the thing that's next in memory. When we're talking about processors and processes, you have very low-level architectural things where you have to worry about, like registers. In this case, we're talking about Intel's x86 processors, and we're running in 32-bit mode. Whenever you see something with the prefix of E, that's an extended instruction pointer. This is for compatibility reasons. They had an instruction pointer that was just an IP that was only 16 bits. So when they went to 32 bits, they gave everything with an E prefix. And then when you go into 64 bits, you have an R prefix. So we're talking about the instruction pointer, and the instruction pointer is a register that points to the address in memory where the next instruction is, the next instruction that we're going to execute. And you manipulate this register directly using calls and branches. And when you're returning from a call, you're putting information into the instruction pointer to resume where you left off. And it's valid only if you're pointing to an executable region in memory. If you start executing parts of memory that are maybe data, then the processor is actually interpreting that data as code, and it will go off into the weeds, and it will likely trigger an exception. And an exception in this case is a segmentation fault. There are other types of exceptions, like dividing by 0, for example. And if you execute invalid memory, if you execute from a location that is maybe, say, the 0 page, then that may not be mapped into a process at all. It may not be data, it's just not there. And if you start trying to run things that are not there, then the processor gets upset and it'll tell the OS to stop the program. So talking about the registers, we have a couple of special purpose registers that are used for keeping track of the stack. And the stack is, like it's called, it's a stack. It's a temporary location to put values in memory. And stacks grow from higher addresses to lower addresses. So this is kind of maybe backwards. What you may be expecting is that you start from the higher addresses, you have saved values that are on the stack, and then you have local values that are stored inside of the stack frame. And between the local frame's end and the beginning is the stack pointer and the base pointer. And you can see that we have a saved base pointer that allows you to do like a linked list of stack frames. And the stack pointers then hold those local variables and those parameters that are used by a function, and it's used to save registers. So what does that mean? So some of the registers that we talked about earlier, like EAX. EAX is a general purpose register that could be used as a result for mathematical functions or mathematical operations. Let's say you're adding two numbers together and you have a result, and you would save those in that register. Well, let's say that a function called another function, and it expects EAX to have another value. You have to store those somewhere, and you would store them on the stack. The stack forms a chain in which functions are called and functions return, and those values that are stored on the stack, like the EIP, is the saved instruction pointer. That's so that we can resume back from where we left off after we return from a function. So when a function is called, those local values and function arguments are pushed onto the stack, and then when the function returns, those parameters are popped, so to speak, off the stack. So let me show you an example of this. So we're calling a function and we're decrementing the stack pointer, and that's our local frame. So we have saved the base pointer that we had from before and the instruction pointer so that we can resume from where we were when we left off. And then that base pointer is then incremented back up, and that establishes our new stack frame, and it keeps going and so on. And so I think you could see where I'm going here with this is if you overflow a buffer that is on the stack, you can actually overflow these values that are saved registers. And one of the ones that's important is the EIP. So let me give you an example of this, and this is written again in C. And it's an intentionally vulnerable example. You probably will not see code that looks like this in the real world, but this is just for demonstration purposes that'll give you an idea about what's going on. And so what we have here is we have a main function, and this main function allocates a buffer called myBuffer. And you can see where it's called char myBuffer 128. So that means that I'm allocating 128 bytes for that buffer. And I'm using this function later on called strcpy. And what strcpy does is it takes two buffers and it copies between them. So in this case, we have a buffer that is called argv, and we're indexing it by 1. That is the first command argument value that we're copying to the buffer. And we've only allocated 128 bytes for this, and my arguments that I could pass to the program can be much longer. In my case, in my system, I had 2 megabytes was the limit. And so you could see that I can actually overflow that buffer far over what it actually is supposed to fit in there. And so what happens when we put more than 128 bytes in this buffer is that we overwrite not only myBuffer, but we start writing into the base pointer and the instruction pointer. So let's say that I'm putting just all A's and I'm passing those into the command. You could see that I'm writing over 128 bytes of A's into the process, and then it goes in and eventually it overwrites the base pointer and the instruction pointer and possibly even data that's after that. And we're taking the control. So what happens is when the process returns, it's going to load the value that is the saved EIP, the saved instruction pointer, and then it is going to put that into the instruction pointer and it's going to start executing. So that's really basically the gist of how a buffer overflow works, is you're taking control of the instruction pointer and you're running whatever, you can actually point to code to run at. And what you could do, if you know where that buffer is, you could point the instruction pointer to that buffer and actually execute it directly. So what was data becomes code. So this is the strategy for exploiting buffer overflows. Your first goal is to control the execution flow. The best thing that you could ever see is that when you run a fuzz test case and you see that the program crashes, and it crashes at 0x41414141. And for those of you who may know or may not know, that is the ASCII value for all A's. So if you're putting a bunch of A's into a buffer, then 41 is the A, and you can actually see that it tries to execute code that is located at 4141, so on. So what you have to do first is when you've done a crash, now you need to figure out where in that buffer the instruction pointer actually is. Where is it in memory? Because I'm going to overwrite a buffer that I may not know the length of. And you may not know what else is in memory maybe after that buffer. So you might have to overflow more to get to that instruction pointer. And a tool that is provided by Metasploit is called pattern generate and pattern offset. And that will create a pattern for you that you can put into your code, your payload, that will show you where in that offset the instruction pointer actually is. And then once you have that, then you can place a favorable address in there to be restored in the instruction pointer when the function returns. And then in that case, you could actually jump into code that you control, like the buffer itself. And also your goal is you don't want to crash the program. So maybe after you're doing your exploit and you're doing your work, you want to return back to the code that was legitimately supposed to be running. So In this case, we're running main, and so of course when main exits, then we're just exiting the program. But in other cases, you may be several functions into the stack, and you want to return back to the legitimate place where you're supposed to leave off. And so you may need to do some fix-ups on the stack to fix the problems that you made when you exploited things, so that you can return to the legitimate function and keep going. And an example of this is, let's say you have a web server. Let's say you're running Apache, and you found a buffer overflow in some part of Apache or some program that Apache runs. And then you wanted to keep that up because you don't want the administrator to notice that something was broken and went down. So you would want to clean that up and make sure that you can continue on. So we've talked a little bit about buffers and the information that you can put in before. We talked about maybe using all A's and having that show up in your saved instruction pointer. Or you want to use very well-defined payloads that are called shellcode. And shellcode does what it says. It's something that if you run, it gives you a shell. And it helps you with exploiting these vulnerabilities. And it's all very platform and OS specific. So if you're running Linux on x86, you're going to have to know that you're going to be running against that kind of system. If you're trying to execute something against Windows and you try to use shellcode for Linux, you're probably going to have a bad time. It's not going to work, and you probably will crash the program. And in the case of shellcode for Windows, Windows is very picky about the shellcode that you can use, and typically you won't call the system directly. You'll use libraries that are in memory. And so there are shellcode patterns, so to speak, that you could use from Metasploit, and there's a command called msfedm, which we'll go into, which allows you to generate these payloads to do certain things. And normally what happens is you don't know really ahead of time what you want to exploit. Maybe you don't know what data is on a server, so what you want is you really want a connection that gives you a shell, that gives you, like, if you're running bin bash or if you're running command.exe on a Windows machine, you want to have that run and then connect it to a socket that will connect back either to you or just open a port. And in the case of where you open a TCP port on the victim side, that's a bind TCP shellcode, you need to listen on a port and then connect to it. And that's not very useful if the machine is behind a firewall, because the firewall could block that connection attempt. So to turn it around, we can actually make a system call home back to the attacker. And so you've got a victim process. The process actually connects out to the attacker through firewall, and that is just a reverse TCP connection. And then in some cases where you have smarter firewalls, you actually have to tunnel that connection over a certain protocol. It could be HTTP or HTTPS, and there's even some DNS shellcode. And then once you have that connection, then you perform the command. It could just be to run a program like a shell or a command.exe. And then if you want some flexibility to that shellcode, you can use Meterpreter. And Meterpreter is a whole suite of shellcode that you could stage that allows you to do things like capturing the desktop. You can capture camera information, so if you want to see what's going on in a room, or if you wanted to even send, you can even play sounds and do things like that, find out what processes are running. So it's almost like a little mini operating system in itself that all happens within a process. So here's how to generate shellcode. This is an example of using a utility called msfvenom. I'm running msfvenom on my Kali machine, and I'm using the payload linux/x86/exec. So I'm actually going to, this is the code that if it runs by the CPU will actually invoke the command /bin/sh, which is the Bourne shell. There are certain characters that I may need to avoid. In this case, I'm doing a stir copy, right? So I would want to avoid a carriage return or a space. And then I would encode that using an encoder called Shikata-Ganai, which is fairly popular. The only thing is it's 32-bit the last time I checked. Maybe at the time of publishing it'd be different, but it is 32-bit. And then we're just showing this payload. So that actually is the shellcode that you would put into the buffer. And then when you jump with your saved EIP into this, you'll actually run this code. So now that we talked a little bit about how to do a buffer overflow and how to do some simple execution of a payload and how to generate shellcode, one of the things that you're going to run into in the real world are defenses against these kinds of overflow vulnerabilities. And this is all an area of active research, and there's a lot of things happening at the same, there's a lot of things happening to help defend against these overflow vulnerabilities, because especially at one time they were incredibly prevalent, and you still see them all over the place. So one of the things you're going to see is object size checking. And object size checking is a feature that you can add to the compiler where whenever you're making a copy from one buffer to another buffer, if the compiler can tell what the size of the buffer is going to be, it will call that function with that size of that buffer, and if you start overflowing that buffer, it will actually cause the program to crash. It'll stop the program. Another thing you may run into is address space layout randomization. ASLR is a feature where every time you run a program, the program's memory will be randomized, so you won't know where your buffers are. You wouldn't know the location to jump into, because every time the program runs, it's randomized in memory. And then the third feature that you may see is data execution prevention. Since we were jumping into the stack before, if we were executing the stack, that's really not something that a process normally does. It doesn't really run from the stack. So unless you specifically tell the operating system to make the stack executable, it will be blocked by the processor memory management unit from actually allowing that part of memory to be executable. One of the ways of working around data execution prevention is do something called return-oriented programming, where you use existing code in what are called gadgets to actually run the code that you want to do. You're reusing the program against itself. And then finally, the last defense is called a stack canary. And all that is it's a value that is stored at the end of the stack. And if you overwrite the stack canary to get to the saved instruction pointer, or you wouldn't know ahead of time what the stack canary's value is. It's random every time you run the program. So these are defenses that you will see in real programs that keep you from doing these kinds of attacks. So you'll need to do other things like being able to find where addresses are by leaking pointers, for example. And so those are some of the defenses that you'll see.